हेलो। हेलो। Hello, Murli sir, are you there? Hello. Uh, so, sorry for the late start today. There was some technical glitch. This is problem solving session 2, and we will be covering the assignments from week 1 and week 2. A solution has already been provided to you. And then we are going to take up some problems from the week 3 content, which has been taught to you. So we'll start with the week 1 and week 2 assignments. A little discussion if you have some doubts regarding the assignments provided in week 1 and week 2. So this was a question asked: how many number of atoms were present in Fahrenheit cell in case of FCC crystal. So we had already discussed such questions during last session regarding how to calculate the number of atoms. At the same time, we also discussed how to calculate the atomic packing fraction and all. So here we have the number of atoms thing in FCC. You can see here in the third row how we have calculated the number of atoms in FCC. So in FCC crystal, what happens is every corner is shared by one atom, which is divided into 8 particular crystals. So every crystal gets 1/8 of that part. So you have here 8 multiplied by 1/8 portion, and then we have one atom at every face. So there are 6 faces, and so 6 atoms, which are again shared by 2 particular crystals sitting side by side. So overall, we have 4 atoms in an FCC crystal. Okay, so now we move to a question called true strain epsilon in terms of engineering strain E is given by. So we have done that last time. We have covered such topics also. So we have one thing called engineering strain, one thing called true strain. So true strain is nothing but some which relates itself to the actual area of cross section at an immediate point of time. So here, if E is the engineering strain given by the ratio of the deformed length to the actual length, the original length at the initial position, then we have epsilon being given by ln 1 plus E. So we find this is the correct option. This formula has been derived earlier, I think. So next question was a perfectly elastic body. So you can see these curves. We were discussing last time that for a perfectly elastic body, there is no plastic region, there is no plastic deformation. And so the first graph is for linearly elastic body, and you can see that only the elastic proportionality limit is there for such a body. And in that case, option B becomes the correct option because you know up to the proportionality limits, that's directly proportional to strain. So after the removal of the load, the body comes back to its initial position. So then we have the next question: in which of the following is not true? So here, you know, 2 types of manufacturing processes are there. One is an additive type of manufacturing, and the other is a subtractive type of manufacturing. So here we have casting, machining, welding, and forming. So you know, casting is always a constant material volume process. Like whatever is the initial volume, after the realization of the product, and the final volume remains the same. There is a volume constancy in casting. In machining, you know, it's a subtractive manufacturing process. We always remove some material out of a product to get the final product. And then in welding, you always know it's a material addition process. Two metals are joined together. There can be an intermediate metal, or it may not be there, but there is no material subtraction. So this is also true. Then the fourth option says forming. So it is a material addition process. No, actually forming is also a constant volume process. The initial and final volume remains constant. Only the shape changes. Okay, so this is the incorrect option here. Then we come to the question called which of the following is true for bonding of solids. So we have like you know about the attractive and repulsive forces very well. So option C says attractive force increases with decrease in distance between two entities. So it is true, right? So with the decreasing distance between two entities, the attractive force must increase, and it reduces with the increasing distance. So this is inversely proportional. So option C is correct in this case. Okay, so then comes this thing. We have discussed the difference between ductility and malleability last time. So here it says, we think we have already covered a question involving ductility and malleability and plasticity, elasticity concepts. So the property which defines rollability of material into thin sheets is called. So of course, that's malleability. Thin sheets are malleable in nature, which can be made of gold, silver, copper, etc. So ductility is, on the other hand, is the property by which material can be drawn. Okay, so that relates to tensile strength, and malleability leads to compressive strength of a particular material. So now we have which of the following is true corresponding for van der Waals forces. So we have, there are intermolecular forces. These intermolecular forces actually are not kind of van der Waals. Actually, these are van der Waals forces. However, these are stronger forces. They're weaker forces. These are still weaker than the other bonding forces. Yeah, that's also true. And these forces are attributed to the rapidly fluctuating dipole moments. Yeah, there is a variable in the particular formula which relates to this particular van der Waals force thing. So all of the options are correct here also. So next we have, if the radius of an atom is in a closed packed hexagonal crystal is r by 2, the length of the edge of the unit cell A is. So we have discussed it in earlier section. If you have understood, it's a pretty easy thing. Like you have to calculate the length of the edge. So we can see one edge is shared by two particular atoms, and each is having a radius r. So our radius r. So we have a total of, here it says the radius is r by 2. Okay, so we have r by 2 plus r by 2 becomes r. So option C is the correct option here. Does anybody have any doubt till now? Okay, so we move to the next question. It says crystal structure defines what? What can you get? What can you realize from a crystal structure of a particular solid? Of course, you can predict the nature of the particular product or particular material in the way if it will be malleable or ductile, it can be deformed, to what extent can it be deformed. All these are defined by the crystal structure. Creep, on the other hand, is something related to temperature at high temperature deformations. That's something not related to crystal structure. Illustration, work hardening, these are phenomena. Only work hardening, strain hardening we have discussed last time. That is not something related to crystal structure. Other these things happen distance depend upon the external force applied on the particular crystal. So ductility is the correct option. So it says how toughness is calculated. So we have discussed earlier session, like what is the difference between this ductility and resilience actually. So uh, sorry, toughness and resilience. So resilience is something you calculate up to the elastic limit of a material, the area under of the stress strain curve up to the elastic limit of a material gives you the resilience. And when you do it in modulus, so we have modulus of resilience in that case. So toughness is something which is related to the stress strain area of the stress strain curve up to the fracture point. Okay, so you can say in generally it is the area under that stress strain curve, the entire area. Okay, so that relates to toughness. And again, per unit volume gives you the modulus of toughness. So this question says, yeah, all the PPTs, don't you have got the link? All the PPTs are being uploaded on the Google Drive and the links are provided, must have been provided from NPTEL authority towards you. Okay. Okay, I'll cross check with them. So it should have been provided. There is a Google Drive link. Okay. So you don't have the YouTube link for the videos too? Oh, okay, okay. Okay, I'll cross check this. Probably in 1 or 2 days you might get that. Fine. So we had discussed water solidus, liquidus, and solvus lines during last session. If you remember from this diagram, you can see that this particular line, which divides a purely liquid phase and liquid plus solid phase in alpha ferritic solid plus liquid. So these lines are called liquidus lines. I mean, the line differentiating pure form of liquid to a mixed form of solid liquid phase. Solidus lines are these ones which differentiate pure solid and solid liquid phase. And solvus lines are something which are differentiating two solids, both solids, but having different microstructures. Like here we have alpha ferrites and there we have alpha plus. Beta maybe some different composition, some different microstructural material, microstructural phase. Okay, so here it says the solidus line defines the temperature dash, which the phases in the diagram are dash. So solidus means the line above which the phases are solid and below which the phases are liquid, isn't it? So you can relate option B from here. So next we have which of the following basically governs the transformation of phases. Okay, so of course there are pressure, temperature, and composition. You can take one constant and find out the relation between the other two, or you can take all the three together and form a 3D graph, as in TTT curves, you know. And then this question was there, like what is 6%, 6.67% of carbon in the iron carbon diagram regards to, and what does 0.8% by weight of carbon regards to. So from the graph you can see around 0.8% we have pure perlite, left of which is perlite plus ferrite and right of which is perlite plus cementite. In the same way, at 6.67%, that is at the rightmost end of the curve, where after which the iron carbon diagram is considered. Here you can see only Fe3C or cementite phase is there. So that relates to option A. Okay. We are talking about this question. What it says?
Yes, sir.
Okay, okay. So I think mm, this diagram is a different diagram. Okay, so in regard to this diagram, the options will be that the solid line defines the temperature, okay, above which the phases in the diagram are. What are you saying? What is your confusion?
Sir, above solid is line, liquid zone is there, no, sir.
There is a composition of liquid and solid.
Yes, uh, but solids are there in bottom line. That is
Yeah,
my confusion.
yeah. So
Because the option is also not given.
yeah,
In
yeah, yeah.
assignment also I have placed none of the above answer, but it shows wrong for me.
Okay, okay, yeah, you are correct. So here, none of the above should be the correct answer actually.
But in assignment one, that I have given that option, but they shows answer is wrong.
Okay, okay. So that must be a technical glitch, I think.
Yes, sir. That's why I have put in a forum also that question. I can't understand, but
Yeah.
I am waiting for that reply also.
Okay, okay. I'll look into that and
Uh,
okay, don't worry, I'll look into that.
okay. Thank you.
Okay. So this is the question before which is stopped. Which of the following is a type of pattern? Casting is very simple. I think you all must know this. Match split pattern, of course. There is nothing called split frame pattern. There is nothing called a drag frame pattern. There is no frame in patterning. Okay, so split piece pattern is there. Skeleton mesh pattern, no, there's nothing like that. Mesh split pattern is the correct option. Now it says which of the following is the best characteristic that a perfectly elastic body holds. So it has a perfectly smooth surface. It completely recovers original and the deforming force is removed. Yeah, so this must be the best characteristics. So B must be the best possible characteristic. Okay, so here we have a question. It says which of the following form is the softest and the hardest? So we discussed in detail about this diagram, TTT diagram, last session. So you already must be knowing that ferrite is the softest and martensite is the hardest. Why? Because ferritic structures are having larger grain sizes when martensitic are having lower grain sizes. Okay, so if we do uh, quickly quench austenite to the martensitic temperature range, then there is no time for the particular for the formation of benite or palite forms, uh, and quick quenching results in formation of very hard uh, phases with small grain structures, so that the dislocations get arrested. Okay, and the particular phases are very hard in nature. So martensite is the hardest, and in the similar for the similar reverse region you can say that ferritic are the softest. And in between phases, palite, benite, a mixture of austenite, palite, austenite, benite, all this form in between. The hardness quotient forms in between ferrite and martensite. Okay, so next we have this, which of the following is the most important consideration in casting? So option A is melting temperature of job and mold material. Of course, melting temperature decides a lot of things, including the possibility of defect formation, the possibility of strength of the particular casting to be formed. Melting temperature also defines like if there will be misrun, if there will be cold shuts which are arising out of temperature gradients, then whether will there be dendrite growth, etc. So melting temperature of job and mold material is of course an important consideration. Then says solubility and chemical reaction between job and mold metal. So of course this is also important because if there is a high solubility between the mold material and the job, then you won't find the required casting in the pure form at all. There will be intrusions between the intrusions of the molten metal into the mold wall and all. Then this gives to defects called red tails, okay, then penetration defects, etc. Then chemical reaction is also important. If there is a lot of hydrogen gas, hydrogen bubble generation, that can lead to hydrogen embrittlements. I hope you know hydrogen embrittlement phenomenon. Then you have thermal properties of job and mold material, of course, that in other words relates to the option. So all of that is correct. So now says which of the following is a type of gating system and casting? So of course, all of them are the gating systems: vertical, bottom, horizontal. Okay, so horizontal is nothing but this parting line gating, in other words. So then you have which of the following is true for interstitial solid solutions? So option A says solid molecules are very small. Of course, this should be small. Otherwise, it can lead to those substitutional solutions. Okay. So for being interstitial solid solutions, the solid molecules must be very small. Then solute occupies interstitial sites of the solvent matrix. Yeah, that's obviously true. So both A and B are correct options. Which of the following contraction type is observed by shrinkage allowance? We have discussed that earlier also. Okay, so a request to all of you guys, kindly don't ask questions from the current week assignment. Okay, not you can ask the concepts, not the direct questions. I hope somebody, I think somebody asked this exact question last session. Okay, this you shouldn't do. So here in this case, option B is the correct because the solid contraction is the most important, which is happening from the freezing temperature to the room temperature. So this, when we give shrinkage allowance in case of casting, we of course take into consideration the contraction from freezing temperature to room temperature in this particular range, because it is having the maximum contraction in nature. He says contraction is related to change of phase from liquid to solid. I told you, right? You have to take care of the maximum contraction. So when in the range up to freezing, from freezing to room temperature, the amount of contraction we are having is really large as compared to the other two types of contraction from liquid to solid. Okay, and during freezing temperature range, to the freezing temperature range. So these are really negligible in compared to the contraction from freezing, which happens during freezing temperature to room temperature. So during designing, we take care of this particular contraction. This is called the solidification shrinkage. Actually, I hope it's clear. Great. So I hope this much was there in the assignment questions. There is one doubt which was raised by one of you regarding that solidus liquidus line question. Okay, I'll talk about that. So now we are going to discuss some topics from this week's lecture, that is third week's lectures. So this is a basic concept. You must know that how there is a how there is the difference between the cooling phenomenon in case of pure metal and the cooling phenomenon in case of a alloy, metallic alloy. Okay, so can anybody of you tell me if you are knowing? I think this has been taught to you. Okay, so the major difference is that the freezing in case of the two, that is pure metal and metallic alloy, doesn't happen in a similar fashion. Like in case of pure metal, you know that the freezing happens at a constant freezing temperature. However, the same thing in case of an alloy happens over a range of temperature. As you can see from the graph, this local solidification time. Okay, so this is different in case of pure metal, which is being shown in the left, and in case of alloy, it's happening over a range of temperature TL and TS. Okay, so what happens as a result is that there is a phenomenon called dendrite formation. Okay, and the zone in which this dendritic formation happens is called as a mushy zone. Okay, this mushy zone is absent in case of what is that called pure metal. Okay, now so why does this happen? Actually, okay, so what happens is in case of alloys, what we have is, I already told you, there is a range of temperature over which solidification occurs. Okay, so there is a compositional gradient, like the whole molten metal doesn't solidify at a particular temperature. So there is a gradient of temperature and which relates to a gradient of composition within the casting. As a result, which happens is there are differential solidification happening within the within the particular casting under consideration, and we find that there are different structures, grain structures that can be columnar grains, there can be dendritic grains, there can be globular grains. Okay, so as a result, what happens? There is a density variation. Okay, because the grain structure is different, of course, that would mean that there is a variation in density, and this ultimately leads to defects and weak structure of the particular product when it is realized out of that material. Okay, so yeah, so in case of alloy, you have to take care of these things. So now we have a question, a numerical question. It says the height of the down screw is 100 mm. Okay, and cross-sectional area at the base. Sorry. Yeah. So it says that the height is 100 mm. So this is a question of about mold filling time. I think this has been covered in the six content, and there must be some assignment question related to this topic also. So it says that cross-sectional area at the base is 300 mm square, and the cross-sectional area of the horizontal runner is also 300 mm square. Now assuming no losses. So losses can be frictional losses and all, which will also cover a type of problem with frictional losses in the upcoming slides. Okay, so here we are assuming that there are no frictional losses. Then you have to calculate the time required to fill the mold cavity of 3 into 10 to the power 5 mm cube volume in the casting. Okay, so you know this relation time equal to V by VGG, this whole thing comes out of uh, continuity equation. Okay, so what happens to be the AG? AG is the choke area. I mean, there are three different types of areas. There can be a screw area, runner area, or gate area. So you have to take the minimum of all. Okay, because that would decide the maximum time required. So here AG is given to be 300 mm square. It is in the runner area here as given. If it was given as a ratio of screw, runner, and gate, you have to take the minimum of all. So here only one area is given, that's of the runners. You take that area, and a total height is given as what it must be given. Yeah, it's 100 mm. Okay, so using that, you can find the mold filling time. That's pretty easy. Okay. So this is the next slide. So I think this question is not correct. Okay, this is the earlier question. So this question is about a screw design. Okay, so all the information are given in this diagram. You have the top boring basin height as 60 mm. You have the screw height as 180 mm. You have the diameter of the high, top surface, that is the larger diameter is 20 mm. Now using that, you have to find out the diameter at the bottom of the screw. Okay, that is at the third point, point 3, it is shown. So this problem comes out of screw design. I think screw design has been taught to you. You can try to solve this problem. For that, I will show you the solution. Yeah, using Bernoulli and at the same time continuity equation, you'll get the result. Uh, try and try, and then we'll solve it. I will show the solution. Uh, are you sure? Please recheck. Okay, let it be. I'll show you the solution. Yeah. So whenever you're designing a screw, the first and foremost thing you have to consider is avoiding the aspiration effect. Okay, do you know what is aspiration effect? Now, aspiration effect is something related to trapping of air bubbles into the molten metal. Now, with uh, reducing height when the metal is poured from the top, it gains some velocity, right? Now, if you keep the area constant, if you keep it as a cylindrical screw, what happens is there is a gap because with increasing velocity, the area of the molten metal, uh, like the molten metal will be falling down, right? So the girth or the area of the falling metal must be reducing with the increasing velocity, isn't it? So what happens is there is a gap between the screw wall and the pouring molten metal. So this happens that it traps some air, picks in some air bubbles, which then becomes porosity in the finalized casting. So you have to take care that you must avoid this aspiration effect. But that is the interest to design problem. So it was seen that cylindrical screw, actually a trapezoidal screw must give you the best result, but because of ease of manufacturing, we use a cylindrical screw. Okay, so here you have this A3 by A2. You can have a look at the diagram. So A3 by A2 must be equal to V2 by V3. This is continuity, right? If you cross multiply, A3 V3 is equal to A2 V2. So A3 by A2 is V2 by V3, which is R, okay, equal to the mold height by the total height. So here the mold height becomes H total 180 plus 60 minus the H2. Okay, so H2 is this height, the screw height. Okay, so this is the pouring basin, isn't it? So this has to be considered. So this is given like that. Now HT minus H2 is the actual HT, this whole thing minus H2 is the actual height. So using that, you can, now it becomes simple. So H2 is 180 and H of the basin, I mean HT minus H2 is then 60. Okay, this is the basin height. This one is the pouring basin. So using that, putting it, you have H total equal to H2 plus HB comes out to be 240 mm. Okay, this total height. So that uh, using this above equation, this continuity equation, you can find out that E3 by 2 equal to V2 by V3. Okay, so E3 by A2 is directly proportional to D3 by D2 square. Pi gets cut off from numerator denominator. Okay, so D3 by D2 square becomes equal to V2 by V3, which again the pouring basin height, which is total height minus the screw height. That is 240 minus 180, 60 actually, this pouring basin height divided by total height. From that, you can find D3 is equal to 14.14 mm. Admin, did you do this in the same procedure? Please have a look. If you want, you can note it down.
Yes, sir.
Okay, so We'll proceed further. So here you have a problem of filling time. Okay, so what happens is that here we have considered the velocity distribution frictional losses things, okay, which are neglected earlier, but this is a more real problem. So here you have that this ladle is being shown. It is having a girth area of 1 meter. We are having a total height of 1.5 m, and this is the height of the molten metal inside the particular ladle. So we have a 100 mm outlet. Okay, now this is an aluminum silicon alloy at 704 degrees centigrade. You have to find out the time required to empty the ladle, and again you have to find the discharge when the ladle is full and half. Okay, so in other words, you can say uh, when the molten metal is at the initial point. Okay, so when the ladle is full, and then when there are only 50% of metal left in this particular ladle. Okay, so can you try? I'll give you the data. You can note it down. Okay, so the data, you can take the density of the molten metal as 2700 kg per meter cube. Okay, and then you can take, you will require the viscosity of the material that you can take as 0.00273 kg per meter cube. Okay, I'll write it down for you rather. So you take density as 2700 kg per meter cube. Okay, and take viscosity as 0.00273 kg per meter second. I think that will be good to go. Yeah, please proceed. So have you been taught this topic? Then you should have some idea, right? No problem. We'll go through it. Okay, so uh, I think you have noted down this diagram. So what happens is, okay, so here what we do is we have to take care of this friction and then the velocity distribution factor, okay, which is given by beta. And this friction shall be considered through coefficient of discharge CD. There is a way to derive CD and which requires a derivation which I will not be going through because that must have been taught in the weekly lectures. Okay, so I will take you to this problem. What we have to do is first look out that how the CD varies. Okay, you have to look at how CD varies, coefficient discharge CD. So what we do is you know that from the earlier problem that the velocity at any particular height is given by root 2 gh, and that comes from Bernoulli equation. Okay. Now, whenever we have to consider CD, then it becomes CD multiplied to root 2 gh. Okay, and now mass flow rate is given by rho AV. Okay, density, okay, into area. So this is the rho m density of the molten metal. N is the area of this particular nozzle, so dia of 100 mm, and then Vn is the velocity of the molten metal coming out through this particular nozzle, okay, which is again given by CD into 2gh. Now, this is one way to find mass flow rate. Another way is that in respect to the ladle. So we have found that with respect to the nozzle, you can also found with respect to the ladle. So in the ladle, we have the molten metal, okay, which is having a density M, an area of ladle, let us consider as A, coefficient superscript L. Now dH dt, that is the velocity of the material, and dH is the height is the h. So when you do the derivative with respect to time, you get the velocity. You know that from mechanics, right? So rho AV gives the mass flow rate again. Now in this case, you get it as rho MAL into dH dt. Okay. Now why there is a negative sign? Because there is a reducing molten metal. The molten metal is coming out of it, and to take care of that, we use a negative sign. Now you have to know what dH dt is to use this particular equation. How do you find that? Again, continuity equation is taken into consideration. Okay, so here you have area into velocity of the ladle, okay, of the metal coming out of the ladle. If you take if you can take 2 points inside the ladle, one, and at the exit of the nozzle, two. Okay, so here you have the area of the ladle AL into velocity of the molten metal coming out through the ladle, which is dH dt, becomes equal to area of this particular nozzle AN, for example, for instance, and the velocity Vn coming out of the metal through the particular nozzle. Okay, so you equate this, and then you replace Vn by Cd into 2gh. Then you can from that find minus dH dt is equal to N by L Cd into 2gh. Okay, now you integrate dH and dt from both sides. You integrate h from hi to hf, integrate time from 0 to tf. What is hi? Initial height and final height and final time. Time starts from 0. Using that, you can find out the time, pouring time, which is root 2 by g, L by n, 1 by cd, root over hi minus root over hf. Okay. Now, what we do is start the problem. Initially, let us check if at all CD plays a role, at all friction plays a role. So take CD equal to 1, that is consider that there is no role of friction. Okay. Then you find the nozzle velocity as root to GH, using root to GH. H, what is H? H is total H is 1.5 meter. Okay. So you use the total H 1.5 meter here. You will find out that the velocity of the nozzle is 5.42 meter per second. Now using this particular velocity, find out the Reynolds number. Okay, because a Reynolds number is what governs if the flow is linear or turbulent. Okay, so here you find out the Reynolds number, density multiplied with velocity through the particular nozzle, and then you multiply the characteristic dimension, the diameter in this case, 100 mm it was given, so it is 0.1 meter, and this viscosity is also given to you. Okay, using that you find the Reynolds number is in the order of 10 to the power 5. So you of course know that this is in the turbulent regime, isn't it? So what happens to be the regime for laminar and turbulent? Do you know? No. Okay, so generally up to 4,000 Reynolds number, we take it to be in the linear regime. Okay, after 4,000, we up to 10 to the power 5 or 10 to the whatever, we go to the turbulent regime. So you can see here it is in the order of 10 to the power 5. So of course it's a turbulent regime. In the turbulent regime, we take out the coefficient parameter for consideration of velocity distribution beta as 1. Okay, and if it was in the laminar region, we would have taken beta as half. Okay, so here beta is 1, and then there is EF, which take care of the friction coefficient. Okay, now EF comes out to be 1/6 of EF as Y, because we have a contraction at the nozzle, okay, sudden contraction. So in case of expansion and contraction, there are some modification of the this coefficient, friction coefficient. Okay. Now, where from have we got EF as 0.45? I'll show you. Yeah. So these are standardized values which have been found experimentally. Okay, so in exam also you will be given, and these things will be provided to you. You don't need to remember. So you can see the fourth option, which is a tapered entry, isn't it? So in our case also, we have a tapered entry, right? See, this one is a tapered entry, right? So okay, so for tapered entry, you have that it is EF gets modified to EF by 6. Okay, so that is what we have considered here. So EF becomes equal to EF by 6. So using that, you can calculate it as 0.075. But what is EFS? How is it 0.45? Okay, so for that you have another graph. Okay. Can you see my screen, by the way?
No, sir.
Now?
Yes, sir.
Okay.
That is not showing, sir. Only problem is.
Okay. Okay, no problem. Wait for a second. I'll show you. Yeah. So now here you see that what I was talking of is the option D. Okay, yeah. You can see this is a contracting nozzle type thing. So whenever there is a sudden contraction, what we do is we reduce the friction factor EF as 1/6 of the actual EF. Okay, and where do we get EFS from? This is from this particular graph. Okay, these things will be provided to you, don't worry. Now here you can see that what was our Reynolds number? It was 5.36 into 10 to the power 5, right? Now it is in the range of 10 to the power 5. So here you can see up to 10,000 we have this third line, and whenever it crosses 10,000 we move to this line and the fourth line. Okay, now you can say where does it cut off? It is almost just above zero point 0.4. Okay, so you take A2 by A1 as 0. What is A2 by A1, by the way? So you can see this area, like what area it is coming out and what area it is flowing through. Okay, so in this case, in our case, what we have is these both areas are almost equal, isn't it? However, this particular area, the ladle area, is quite large in terms of this area, this nozzle area. So in other words, we can take out the thing that area of the nozzle is almost negligible in terms of area of the ladle. So that thing counts to that thing counts here as A2 by A1. Okay, let's take A2 as the nozzle area and A1 is the ladle area. So ladle area is quite large in terms of the nozzle area. So the overall A2 by A1 ratio we take to be almost 0. Okay. Now here at A2 by A1 0, we directly have the y-axis, the EF axis, and at the Reynolds number of 10 to the power 5, which is almost infinity. I mean, not infinity, but above 10,000, we consider it as very large. Okay, so for that we have around 0.45 of EF. Okay, and then for sudden contraction we divide it by 6. These are standardized rules. We find the net friction factor now is EFS divided by 6, comes out to be 0.075. You can see here. Okay, now comes so you can see that it is very low, isn't it? So frictional losses are almost negligible. isn't it? So in other words, friction coefficient is an indicative of frictional loss or friction factor. Okay. So CD, there is a particular formula for CD, which is given as uh, which is given as uh, 1 plus EF. Okay, that is the friction coefficient, plus you have this thing called mm, friction factor, 4 times of friction factor in bracket L by D. L is the length and D is the dia of the nozzle. And then you have L by D equivalent whenever we have contraction or expansion to take care of that, whole to the power minus half. That particular thing must have been derived. Okay, you can go to the lectures, you will find the derivation of this CD. Now what happens here, the friction coefficient is too low, 0.075. So we can say that frictional losses are almost negligible. So in CD, we are left out with only beta term and that EF term, okay, which we have just found out above. So the rest of the things gets cut off. Now the beta is 1 for turbulent regime and EF has been found out to 0.075. Putting this in the formula for CD, we found CD is 0.96, which is close to 1, which means that CD has a very, which you can quite understand here, that CD is almost close to 1. Initially, we had taken CD as 1 here when we didn't consider the friction thing. Now, considering friction thing also in the turbulent regime, we find CD is close to 1. From that, one can infer that CD, that friction plays a very less role in this particular case, isn't it? So to verify that, we have taken a laminar case. Okay, in a laminar case, we take RE as almost 0. Okay, so anything between of a low Reynolds number is always a laminar flow. Okay, in case of laminar, beta happens to be half, 1/2, and EF we have again found out from, I'll show you. So you can see that for laminar flow, R is almost 0. Okay, so this fast line, in the first line, you can see it is almost equal to 0.82, isn't it? So using that, after dividing by 6, whatever we are getting, what was we getting? Yeah, it is almost equal to, it is greater than 1 and less than 1.2, sometimes somewhat in between, maybe 1.1 or so. You divide it by 6 and get somewhat like 0.82. Now, see, this was the formula I was talking of. Okay, in this case, because we have a very low EF, friction coefficient EF, we have this friction factor very low and this whole part gets cut off. Okay, we have only beta, we have EF, whole to the power minus of half. So using that, we find CD as 0.69. Now this coefficient of discharge is not negligible, right? So we see that in case of turbulent regime, we found out CD is close to 1. That's negligible. In the other case, in laminar, we have CD close to 0.69. Now that should be taken into account. Okay. Now this was our case. This was our actual case, isn't it? And this is a defined case. This is a considered case. We just used it to verify if our CD variation is true. Now we have considered another case in which HB equal to 0.05 meter, anywhere in between 0 and whatever the total height, in this case 1.5 meter, we have taken, isn't it? See, 1.5 meter. You can take anything in between, right? So we have taken here 0.05 meter and considered and assumed CD1. And in the same way, we have reiterated it, find the velocity, find the Reynolds number, corresponding beta, corresponding EF from the graph of EF versus A2 by A1, which I've shown you. Then you find CD is 0.96 again. What does that mean? What is the Reynolds number here? it was almost equal to 98,000, much higher than 4,000. It is again turbulent region. So we find CD 0.96 again. So can you see the trend? Like whenever we go to a turbulent region, we find that CD is close to 1. Okay. Now our problem, actual problem was this. Okay, actual dimension was h 1.5 meter and found CD as 0.96. So CD remains constant throughout. Now take CD as 0.96 and find out the mold filling time as using this formula. This was found out earlier. Here you can see. So this TF you use and find out the mold filling time. Okay. Yeah. So this has two variables, or three variables actually. Height is 1.5. Okay, and then because the entire mold gets down, entire mold becomes empty at some point of time. So it take the final height as 0. Final molten metal height in the mold is 0. So that initial height was 1.5. We have used that. CD is 0.96. Okay, and this is the ladle area, which we find out from here. It had a dia of 1 meter. Okay, the dia of 1 meter, and the nozzle had a dia of 100 meter. So 100 meter means 0.1 meter. So using that, we find out the ladle area, the nozzle area, put it here, and this is 2 by g, root 2 by g, and all these variables gives you the mold filling time of 57.6 seconds. Okay, and then what we do, the other question was to find the mass flow rate discharged through the nozzle. How do you find it? It is rho AV, isn't it? So the nozzle area is 7.85 into 10 to the power minus 3. You can see here, this is the nozzle area. You put it here. This is the density of the molten metal. This is the velocity, okay? CD into root 2g into total height, 1.5. So this gives you the mass flow rate as 98.73 kg per second. Another question was, you have to find out the this discharge when the ladle is full, which you have found out, and then there is one it was half. I mean, it becomes half means what? The ladle is half filled, so the height comes down to 1.5 by 2, isn't it? So we have done it here. So the density remains the same. And then 0.96 is the CD, and root 2g height becomes half because the model is now half filled. The ladle is now half filled. So the height of the ladle becomes half of the total height, initial height, which is 1.5 meter, 0.75 meter. You put it here and find out that the mass flow rate of discharge is coming out to 69.81 seconds. So you can see the discharge is decreasing, isn't it? When the mold was full, the discharge was 98.7, and when it becomes half, the discharge comes out to almost 70. Yeah. So that is related to the height. Okay. So yeah, this is it. Now, hope you have got it. If you have any problem, you can ask me. Yeah, sure.